Hello and welcome back. Today we're going to be doing something different and helping out the folks on r/electronics, where I came across this post where this user needed help counting to 4 on a 7-segment display. So we're going to do the best we can, but before we jump into it, why don't you all just smash like and subscribe. Now to count to 4 on a 7-segment display only requires 3 bits of data. This is because in binary, you can represent 2 to the n combinations, where n is the number of digits, or bits, that you have. So if we use 3 bits, we have 2 to the 3 possible combinations of bits, and therefore we can count 8 different combinations. And so here is a table that we can use that has every single combination of 3 bits, and you can see that we can count from 0 to 7. And because we want to make this as simple as possible, and we only need to count to 4, we're just going to delete the rest of the table. So now that we have our table, we want to express each of these 5 combinations as a product term and make it equal to 1. And we'll see why this is important later, but what this means is that we'll be rewriting each of these in terms of A, B, and C, so that when we multiply them together, we get a 1. So in our first case, when we want to display a 0, all of our inputs will be off. And so to make our product term, we will have to invert all of our variables. This will give us not A multiplied by not B multiplied by not C, which will be 1 times 1 times 1, and this will give us 1. And in our next case, we simply will not invert the C because the C is already equal to 1. So in this case, we have not 0 times 1, which also equals 1. And we will repeat this process for the rest of our combinations. And this is going to come in handy when we fill in our Kmap maps. But before we can fill out our Kmap maps, we need a bit more information. So what we've done is we've provided a name for each of our segments, A through G, in lowercase letters, because we need to know which segments will be on in which of these 5 scenarios. So if we start in the first case, when all of our inputs are equal to 0, we want these 6 segments to be on. So we'll list them here in the middle. This is to say, if not A times not B times not C equals 1, then we want to turn on all of these segments. And when we want to display a 1, we only need these 2 segments to be on. So we'll write it down in the middle here and say that when not A multiplied by not B multiplied by C is equal to 1, then we want these 2 segments to be on. And we want these 5 segments to be on when we display the number 2, these 5 for number 3, and these 4 for number 4. And now that we know under which circumstances we want each segment to be on, we can start expressing each segment as a sum of products. And to understand what a sum of products is, we're going to start with this A segment. As we can see, our A segment should be on in these 3 scenarios according to the data we've created. In other words, we want the A segment to be on when we display a 0, a 2, or a 3. This means we have 3 separate product terms that all represent the segment A, as we want the A segment to turn on if any of these product terms become true. And that's why we made the product terms equal to 1. So if we combine these 3 product terms together using the OR function, represented by the addition symbol, we now have a sum of products that represents our segment A. This way, if any of these 3 product terms become true, A will also become true because we're using the OR function in between each product term. So if the first or second or third case is equal to 1, then so will A. In all other cases, A will be equal to 0 because all of these product terms will be false, and therefore so will A. So using NOT gates, AND gates, and OR gates, we could build this expression in real life and hook it up to our segment A, but that would be too many components. So we're going to simplify this and make it so that we need less logic gates. But first, we're going to make a sum of products for all of our other variables. Then we'll move on to the Kmap maps, which we'll use for simplification. And now we'll do the same thing, but for segment B. And we can see that B only turns on in 2 cases, when we want to display a 0 and when we want to display a 4. In all other cases, B should be off. So this product term will be equal to 1 when all three of our inputs are 0, and this product term will be equal to 1 when only our A input is equal to 1. And these two input states represent our 0 and our 4. So we can quite simply join these two terms together with an OR function and say if either of these cases becomes true, then we want to turn on B. And this will be the sum of products that will represent our B segment before simplification. So we'll remember this for later and move on to C. And so for our C segment, because we're only counting from 0 to 4, we can see that the C segment is actually going to be on in all 5 of these cases. So we could make a sum of products for C, but to make life easy, we're just going to say C is equal to 1. And this is because there is no digit between 0 and 4 that we want to display, where this segment will actually be off. So we're not even going to connect any logic to our C segment input. We're just going to connect it to a high signal because we're only counting to 4. So now we'll move on to the D segment, this one in the middle. And we can see that we only want the D segment to light up when we display the digits 2, 3, and 4. So just like we did for segments A and B, all we need to do is combine these three product terms together, separated by the OR function. And this way, if either of these product terms becomes true, then so will segment D, if we connect it to this logic. And we'll do the same for E, F, and G. So now that we have a sum of products expression that represents each of our variables, we can use Carnot maps, also known as Kmaps, to simplify them to the most basic form. So the first thing you'll notice is that this Kmap has 8 different squares. This is because we're using 3 different variables, which can be arranged in 8 possible combinations. The next thing you might notice is that this A and B sequence on the top is out of order. That's because for a Carnot map to work, you need to use something called gray code, in which, in between subsequent values, only one bit changes at a time. Otherwise, the Carnot map won't be effective. So keeping in mind that our variable A is the most significant bit and has a weight of 4, and that our variable B has a weight of 2, and that our variable C is the least significant bit and has a weight of 1, we can assign a value to each of our cells as follows. But because in this project we're only counting up to 4, we can actually take these 3 cells and we'll mark them each with an X. And we'll call these 3 cells our don't cares. And this is one of the advantages of a Carnot map, and you'll see how this helps us later. So now we have all the information we need to start simplifying our sum of products expression for segment A. So the first thing is to put a 1 into each square for each of our product terms. And because this expression has 3 product terms, we're going to put 3 1s into this grid. We'll put the first one in this square because A bar, B bar, C bar is represented by 0, 0, 0. The second one will go in this square because the 0, 1 represents the A bar B, and this 0 represents the C bar. We'll then put a 1 into this square because it represents A bar, B, and C. And we'll put a 0 in all the remaining squares. So now that our Kmap is filled out, we can start making our groups. And the goal is to make as few groups as possible and make each group as large as possible. And we'll be finished when every single 1 is inside of a group. And we're not allowed to include zeros in the groups. And the nice thing about these don't care cells is that we can include them in groups if we want to, but we don't have to. And one important thing to note is that our groups have to have a size that is equal to a power of 2. So the biggest group we can make right now is by circling these 4 cells. And we can call this group B. This is because in all 4 of these cells, B is equal to 1, regardless of what A is equal to, and regardless of what C is equal to. So by making a group of 4, we can eliminate 2 variables. So now all we need to do is find a group for this final 1, and the biggest group we can make is a group of 2, because our groups have to be a square or rectangular shape. And we can call this group A bar, C bar. This is because both A and C are equal to 0 all throughout this group, regardless of our input B. So now that we have all of our 1s inside of a group, we can say we're done with this Carnot map. And our final expression is A is equal to A bar and C bar, or B. And so this is the simplified expression we can use to represent our above equation. So now we can use the Kmap to simplify our segment B. We've placed a 1 in this square, which represents this product term. And we've done the same with this square here. And because we still don't care what happens in the case of an input of 5, 6, or 7, our don't care squares will keep the same. And so we'll fill a 0 into the 3 remaining squares where we want the output to be off. So we want to circle both of these 1s with as few groups as possible and using the largest group size we can. And here's where we can take advantage of the fact that a Kmap actually wraps around on itself. So these two cells on the left actually extend out of the page, wrap around, and come in through the right side to meet these two squares. And this is also true vertically, but it doesn't matter in our case because we only have a height of 2 and these cells are all touching top and bottom anyways. So using this handy feature of a Kmap, we can actually circle this 1 here and place it in a group of 2 with this one here because these cells are connected together. And we can call this group B bar, C bar because in this case, both B and C are equal to 0 regardless of the value of A. And because we only needed one group to circle all of our 1s, we're actually done with this Kmap. And we can say that this expression up here is equal to this expression down here. So we're going to remember this expression down here for later, and we're going to move on to the Kmap for segment D, because we've already said that C is equal to 1, and we don't need to make a Kmap for it. So for our D Kmap, we've placed these 3 1s, which correspond to our 3 product terms. We've placed a 0 in the remaining 2 cells, and left our don't care cells the same. Now starting from the left, the biggest group we can find would be this group of 4 right here. We couldn't group all 6, because again, the groups have to be a power of 2 in size. We're going to call this group B, because in all of these cells, B is equal to 1, regardless of the values of A and C. And to get our final one into a group, we'll do the same thing, but with these 4 cells. And we're going to call this group A, because in all 4 of these cells, A is equal to 1, regardless of the values B and C. And because now we have all of our 1s in a circle, we're done with this Kmap, and we could say that D is equal to B or A. And for our E Kmap, we only have 2 1s filled in, because we only have these 2 product terms. So we'll make the remaining cells, besides our don't cares, equal to 0. And we can circle both of our 1s into a single group, and we can't make this group any bigger than 2 cells. So we can call this group A bar and C bar, because in both cells, A and C are equal to 0, regardless of the values of B. And because we've already managed to circle all of our 1s, we can say that we're done, and that the above expression simplifies to what we have below. So for our F segment, we'll place a 1 into each of the cells corresponding to each of our product terms, and we'll make the last cell a 0. So we want to make our groups as big as possible, so we're going to start with this group of 4 that forms a straight line across the bottom. We're going to simply call this group C, because C is equal to 1 in this whole group, regardless of our A and B inputs. We can make another group of 4 by using the same trick we did before, by wrapping around from the left to the right. This way we have all of our 1s circled in only 2 groups. We can call this second group B bar, because in all 4 of these cells, B is equal to 0, regardless of the values A and C. So we have all of our 1s circled, so we can say that F is equal to C or not B. And we don't actually have to make a Kmap for our G segment, because this is the same expression that we had for A. So we'll just connect the logic we have going to A to G as well, because both of these segments will always be on and off at the same time if we're only counting to 4. So here's a list of the simplified logic we need to turn on each of our segments. And this is based off of our 3 inputs, A, B, and C. And this is all the time we have for this video, so we'll get working on part 2 right away, where we're going to explore how to actually implement this onto a physical breadboard. So please like and subscribe, and leave a comment if you have any questions, or if you'd like me to cover another topic. Thank you.